Welcome to the Explainer. Today, we are getting our hands dirty. We're moving from theory straight to the job site to break down the critical, on-the-ground construction details of India's Code for Earthquake-Resistant Buildings, IS 4326. So forget the abstract principles for a moment. This is all about the specific actions that make a building safe when the ground starts to shake. This is where the blueprint hits the rebar. Now, if you joined us for part one of this series, you'll remember we covered the big picture, the why. We talked about the core principles and the theory behind seismic design. Well, today, in part four, we're shifting gears completely. We're moving from the drawing board to the construction site. We're leaving the why behind to focus exclusively on the how, the practical nuts and bolts details from the code that actually transform a design into a resilient, life-saving structure. This is for the site engineer, the one who actually has to build it. So here's our roadmap for this explainer. We'll start by bridging that gap from principles to practice. Then we're going to build our understanding from the ground up, literally, starting with foundations and how we keep buildings from bumping into each other. We'll spend a good chunk of time on the real details of strengthening masonry, which is the backbone of so much construction. And finally, we'll look at the specific rules for modern precast methods and classic timber frames. All right, let's get started. Right, let's get into it. Our focus today is squarely on the practical clauses for conventional buildings. And look, these aren't just abstract guidelines. These are the specific, non-negotiable rules that a site engineer, a contractor, and a builder have to follow to the absolute letter. This is all about making sure a building doesn't just stand, but stands strong when it counts the most. Okay, before we dive into the real nitty-gritty, let's just do a super quick refresh of the 5 core principles that drive every single rule in this code. First, lightness, because less mass means less force trying to tear it apart. Then, continuity, making sure everything is tied together. Symmetry, which helps avoid deadly twisting motions. Ductility, so structures bend before they break. And, of course, foundation integrity. Keep these 5 ideas in your head because every single construction detail we're about to look at is a direct application of one of them. So with those principles in mind, let's start where every project does, at the foundation. A building's resilience really begins before it even rises above the ground. We're going to look at 2 critical things here. First, how we stop buildings from smashing into each other during a quake, and second, how we make sure their foundations act as one single, stable unit. The first rule of seismic safety, especially in dense cities, is actually pretty simple. Give your building some personal space. During an earthquake, every structure sways at its own unique rhythm, and if they're too close, they're going to crash into each other, a really destructive phenomenon that we call hammering. The separation section is that engineered gap, designed specifically to prevent this from happening. So, how much space is enough? Well, the code doesn't leave you guessing. As you can see right here in Table 1, it's very specific. And what's really interesting is the logic behind it. A stiff, rigid box system only needs about a 15mm gap per story. But a more flexible steel frame, which is actually designed to sway more to get rid of that energy, it needs double that space, 30mm. So the code is directly linking the gap to how the building is expected to behave. And here's the key part. No matter what you calculate, the minimum total gap can never be less than 25mm, period. Now, here's something that sounds like a total contradiction. Above ground, the rule is separate, but below ground, especially on softer soils, the rule is the exact opposite, connect. It sounds a little weird, right? But it's absolutely essential. Tying foundations together is the only way you can prevent something called differential settlement. That's where one part of the building sinks more than another during shaking. And believe me, that can be catastrophic. Clause 534.4 is crystal clear on this. If you're building on soft soil with separate, isolated footings, you must connect them. These reinforced concrete foundation ties create a rigid grid under the ground. This grid forces all the individual footings to move together as one unit, preventing them from shifting around on their own. The code even gives you minimums for the size and the steel, so there's really no room for error. This is how you turn a bunch of separate footings into a single, stable raft. All right, let's move up from the foundation to the heart of so many buildings in India, masonry. The safety of a brick building doesn't actually come from the bricks. It comes from the hidden skeleton of reinforcement that you build inside it. And this is where meticulous on-site detailing isn't just good practice, it's the literal difference between a safe home and a potential collapse. Think about it. Every door and every window is basically a wound that you have to cut into a wall's structural fabric. In a solid wall, the stress flows smoothly down from the roof to the foundation. But an opening completely interrupts that flow. It forces all that stress to concentrate dangerously right at the corners. This creates massive weak points and just tanks the wall's ability to resist the side-to-side shearing forces of an earthquake. So to manage this built-in weakness, the code gives us very strict geometric rules, laid out right here in Table 4. Let's make this real. Look at that third line, minimum pier width. For a building in a high-risk zone, this means the solid section of brickwork between two windows has to be at least 560 millimeters wide. This is not a design suggestion, it's a hard limit to make sure there's enough structural meat left in that wall to actually handle the load. And this brings us to a classic on-site problem. What happens when the architect's vision for this beautiful, huge window clashes directly with the strict structural rules we just talked about? Do you have to scrap the design? Well, thankfully, no. The code actually anticipates this conflict and gives us an engineered way around it. The principle is really simple. If you break the rules, you have to add extra strength to make up for it. If your window is too big or too close to a corner, you are required to strengthen it. As this illustration from the code shows, you have to build a reinforced concrete frame with both vertical and horizontal steel directly into the masonry around that opening. You are literally replacing the strength you took out of the brickwork with the tensile strength of steel. So beyond just dealing with openings, the code requires an entire system of strengthening elements, that hidden skeleton we were talking about. But the amount of reinforcement isn't the same for every building. It depends completely on the building's seismic risk category. So how does a builder on site know exactly what they need to do for their specific project? The answer is Table 5. This is the definitive checklist. Let's walk through a real example. Imagine you're building a 2-story house in a Category D seismic zone. This table tells you, with zero room for interpretation, that you must provide strengthening arrangements A all the way through G. That's not a menu you get to pick from. It's a complete, mandatory system that includes everything from the lintel and roof bands to vertical steel at all the corners and openings. Now, of all those strengthening elements, these horizontal bands are probably the most important. The best way to picture what they do is to think of the steel hoops on a wooden barrel, right? Those hoops are what hold all the individual wooden slots together. In the exact same way, these reinforced concrete bands circle the building, tying all the walls together and forcing them to act as one single rigid unit. This is what we call box action. And the code gets incredibly specific. Table 6 doesn't just say, hey, add some steel. It tells you the exact diameter and the number of bars you need based on how long the wall is. But here is the one detail that can make or break this entire system on site: continuity. That steel is completely useless if it's not continuous. As you can see in the corner detail from Figure 11, the bars have to be properly bent and lapped at every single corner. If you break that link, the entire hoop fails. The second part of this hidden skeleton is the vertical steel. So if the horizontal bands are the hoops, this vertical reinforcement acts like stitches, tying the building together from the foundation all the way to the roof. As the code spells out, these steel bars are placed at every corner and every wall junction. They're set into little pockets left in the brickwork and then grouted solid, creating a super strong bond. This is what stops the walls from peeling apart at the corners during shaking. Okay, let's switch gears to a more modern way of building, using precast floor and roof units. They're great for speed and quality control, but they have a unique seismic challenge. How do you get dozens of separate concrete planks to act like one single solid slab? The goal is to get what we call diaphragm action, where the entire floor is so rigid it can transfer horizontal earthquake forces to the main walls without breaking apart. Just like with masonry, Table 8 gives us a nice, clear checklist. And you'll notice a pattern here. The requirements get tougher as the seismic risk goes up. For a lower risk building, a tie beam and some deck concrete might be enough. But for a high-risk Category D or E building, you've got an extra critical step. You have to physically anchor the steel from the precast units into that perimeter tie beam. And look who's back, a recurring hero in our story, the continuous reinforced concrete beam. For precast systems, we call it a tie beam, and it is the single most critical element. As Clause 9.2.3 explains, this is the beam that binds all those individual precast pieces together. Just think of it as the strong, reinforced concrete rim that turns a bunch of separate pieces into one unified whole. So let's just walk through how this is done on site, because the process itself is a masterclass in integration. First, the precast units are laid down. Second, that all-important perimeter tie beam is cast, locking them in place. Third, In those high-risk zones, the steel from the units is physically anchored into that new beam. And finally, a layer of reinforced concrete topping is poured over the whole thing. It's this systematic four-step process that turns a floor made of separate pieces into one single monolithic, strong diaphragm. And finally, let's touch on one of the oldest and, in some ways, most naturally resilient building materials out there, timber. Its high strength-to-weight ratio is a massive seismic advantage. Remember our very first principle, lightness? But that natural advantage is completely wasted unless the structure is properly framed, braced, and anchored so that it's rigid. The code details two common ways to do this. On the left, you've got modern stud wall construction. It's a pure timber frame, stiffened up with diagonal braces and covered with a lightweight sheathing. On the right, you have a more traditional brick-knobbed frame, where the spaces between the timber members are filled in with masonry. This adds both rigidity and mass to the whole system. But here's the thing. No matter which method you use, the core principles are identical and should sound really familiar by now. It's all about strong connections, diagonal bracing to stop the frame from wobbling, and making sure there's continuity of all the structural parts. And most critically, as you can see in this detail, the entire lightweight timber frame has to be securely anchored to its foundation. Without that solid connection, the top and bottom would just move independently and the whole thing would fail. So as we've moved from foundations through masonry, precast, and timber, a really clear pattern has emerged, right? Seismic resilience isn't about one magic bullet. It's a whole philosophy built on a few key actions. It's about physically tying elements together. It's about an obsessive attention to the continuity of steel. It's about creating rigid box action so that everything moves as one. And it's about building ductility into the details, so the structure can absorb energy without a catastrophic, brittle failure. So the most important takeaway is this. The rules and details in IS 4326 aren't just bureaucratic guidelines. They are the absolute minimum requirements for life safety, written from decades of calculations, experiments, and often painful lessons from past failures. The code gives you the blueprint, but real resilience isn't built in an office. It's built on site, by meticulously executing every single one of these details. So the final question for every engineer, contractor, and builder out there is, are you just following the lines on the drawing, or are you building to the letter of the code? Thanks for joining this explainer.